We have already seen in the last example, in the last video, about new kind of setup, two-factor setup, and we shall continue with the analysis of that using a computer. But before that, I will spend this video to understand something which is much more generally applicable other than simply two-factor models and something that really brings to the fore the statistical aspect of linear statistical models. It is not just about doing some linear algebra and learning some computer syntax. So what is the statistics involved in it? And there are four basic principles of statistics that we have to use here, that we have been using, but I just want to make them clear. And these four things are called: number one, the concept of control; number two, the concept of confounding; number three, the concept of blocking; and number four, the concept of randomization. The first concept, namely the concept of control, is this. Whenever you have a black box system, you have some input and you have some output, and you want to see whether the input has any influence on the output, always make sure that you are comparing one level of the input with another. Do not just say that I have put some input and I have got some output, so whenever I will put this input, I will get that output. That is not necessarily true. So the input is causing the output, or it is the input which accounts for the change in that output. You cannot make such a statement. Let's take a very simple example. Suppose I take some medicine, say I am ill, and I take some medicine and I get well in 1 week. And I say, you see, the medicine worked wonder. I just became well in 1 week. You can't say that. You can say that only when you compare it with someone who has a similar illness and did not take the medicine. It's quite possible that that guy also became well within the same period of time. So in that case, your medicine had actually no effect. It is possible that that other guy got well within 2 days, while you, under your medication, took 7 days. So in that case, your medication is actually something which is bad. So that is why I am saying that whenever you want to say that some input has an effect on the output, make sure you compare it with a benchmark value. Now here is sort of a humorous way of remembering it. Suppose you go to a room and you find that there are two switches. One is the on position and the other is the off position. And you find that there is also a bulb, a light bulb, which is on. And based on that, you want to guess whether which switch is actually controlling that light bulb. Now you just look at it, you see this switch is on, this switch is off, so you immediately conclude that this must be the switch that controls it. So what you do is that you try to turn this light off, so you flick this switch off. And you find that the light does not go off, it remains on. You immediately understand that this switch is really not controlling it at all. Now you try this one, this looked like off, so you flick this fellow and immediately the light goes off. So now you understand that actually this switch was controlling the light. Now why did you arrive at the wrong conclusion when you just looked at the two switches without touching them? Because you compared the value of the switch on, originally it was on, and the value of the light. They were both on. So you thought that since this is on and that is on, this on is causing that on. But when you changed it, that is, you compared how the output behaves when you are flicking it. So you are comparing its on position with its off position and looked at how the output changed. Then you got a much better idea about the input-output relation. So do not compare value of the input with value of the output, but compare the change of the input with change of the output, that is a much more reasonable way of coming to a conclusion. Now, in various studies, you need to do that. You must set a benchmark and see if I change the input from the benchmark to a new value, how things change. Say, for example, you are interested in finding whether a particular medicine has got any effectiveness in curing some kind of disease. Then do not just say, here I took a bunch of people, I have applied the medicine to them and they got well, or 80% of them got well. That's not enough. You must start with two groups of people who are more or less identical, have same kind of disease, and then you should take these two groups of people, and for one group you will apply the medicine, and for the other you will not apply the medicine. Compare how these two groups differ in terms of their getting well. Now, sometimes it so happens that you give the medicine to one group and not to the other group. Now, the group that gets the medicine has a feel-good factor. We have got a medicine, so we are going to get well soon, and this feel-good effect sometimes helps them to get well better. It is not really the chemical effect of the medicine. In order to get rid of this, so that we can really understand what is the effect, the true chemical effect of the medicine, what we do is that we give to this other group, that is often called the control group, that is the benchmark group with respect to which you are comparing, that is the group to which you have not given any medicine. What you do is that you give them some medicine. That's something that just looks like the real tablet, but it does not have that chemical in it. And this is called placebo. So you give placebo to the control group, something that looks like the medicine, so the patients do not really know that they are not given the true medicine, but you, the researcher, know. And this is called a blind experiment, because the patients are kept in the dark as to whether they have got the real medicine or not. Everyone sees that they are getting identical looking pills which they take, and the medication, the true medication or this placebo medication continues for say a month, and then diagnostic measurements are made. But the researcher knows that some people are actually not getting the true medicine. Now we can compare. So the group which you are using as a benchmark, that is called the control group. And you can never apply linear models meaningfully unless you have a control group. So the linear algebra doesn't care about that. It just cares about y equal to x beta plus epsilon. The computer does not care about that as long as you can write a suitable formula in LM. But the statistics will become meaningless unless you have a control group to compare the thing against. And I talked about the blind experiment where the patients are kept in the dark as to whether they have got the true medicine or the placebo. There is another version which is called double blind experiment, where the experimenter is also kept in the dark, so that when he or she is taking the diagnostic measurement, he is not getting biased as to, I know this fellow has got a placebo, so I know that he cannot get well. So everything is kept in the dark, but the true identities are written down somewhere, possibly generated randomly using a computer and kept in a secure place. So after all this data has been collected, then that file is opened, and now we know who is placebo and who is the true medication. So that is called a double blind experiment. It is blind on part of the patient, it is blind also on part of the doctor. The next concept, the concept of confounding, is a very important one, and it is something that's little more than common sense. Say I am very ill and someone has given me an allopathic medicine saying that this is a very good medicine, and someone else has given me a homeopathic medicine saying that that is a very good medicine. Now I want to know which one is a good medicine. So what I do is that I swallow both the medicines. I take the allopathic medicine and the homeopathic medicine, and after 3 days I get well. Now from this, can I really say that the allopathic medicine cured me? No. Can I say that the homeopathic medicine cured me? No either. It is quite possible that the two chemicals mixed together actually cured me. It is quite possible that the allopathic medicine actually cured me, the homeopathic medicine has no effect, and the similar thing can be said about the homeopathic medicine. It is quite possible that I would possibly have been cured by only one medicine, possibly have been cured by no medicine at all, and these two medicines kept me ill longer than I should have been. In short, you cannot make any decision regarding these two medicines simply because you took them together. What you should have done is to apply it to different persons of identical nature. Only then you can say, well, the guy who got the allopathic medicine got well in 3 days, and the guy who got homeopathic medicine got well in 2 days, and now I can compare. So this is the idea of confounding. So confounding means if you apply two things, change two things simultaneously, then any change in output cannot be clearly attributed to this input or that input. Try to change the inputs one at a time. If you do not do that, then the two inputs are said to be confounded. Now that is a concept which is often present in various disguised forms. So let's take an example like this. It becomes tricky, especially when you are confounding between a treatment and a factor and a control factor, or between two control factors, that is factors which are beyond your control. Let's take this example. In many cases, many people will say, especially in this part of the country, say West Bengal, that, oh, I have seen the Muslims, they are very, very uncleanly people. So if you go to any place where infested by Muslims, they are very, very dirty place. And that will be indeed borne out by actual fact. So if you visit places where you will see there are many, many Muslims, they are generally very dirty places. There's no doubt about that. So it seems to bear out this allegation that somehow this religion is connected with uncleanliness. So basically, roughly speaking, we have such a black box in our mind where a person is the unit, and we have got religion as the input, and we have cleanliness as the output. Of course, this is just a non-mathematical example. I am not going to go into how you measure cleanliness as a continuous variable, etc. Suppose religion has got two levels, say Hindu and Muslim, and this is cleanliness. And if you just go about, say, various parts of Kolkata, various parts of West Bengal, you will really see that this Hindu-Muslim thing, that generally the Muslim infested parts are very uncleanly, and the Hindu infested parts are generally cleaner than that. However, if you look carefully, you will see that there is yet another factor which is playing a role, and that thing is the educational level. Now, the most of the Muslims that you see in and around Kolkata, they also happen to be of the poorer class and low education group class, because as it so happens in this part of the country, only the very poor people are generally Muslims. So the Muslims are generally poor people, they cannot afford good education. As a result, when you are looking at a general Muslim, so to speak, most of them, you are looking at people with low educational level. So it is quite possible that the uncleanliness that you see is because of low educational level. Whereas when you look at a bulk population of Hindus, there are low education people as well as higher education people. So the difference that you see has nothing to do possibly with religion. It can be explained using the difference in educational levels. In this case, these two factors are basically confounded when you just do an observational study, just like social study. You observe whatever you get to observe. In that case, you will see that whenever religion becomes from Hindu to Muslim, the educational level also generally falls. So it is basically like this. Say I take 3 educational levels, I call them low, medium and high, and Hindu and Muslim. So I have got 6 cells. So I can draw a meaningful conclusion only when I know all these 6 cells are nicely represented. But if you just go about this part of the country and observe whatever you can observe, in that case you will see that typically only the purple boxes are represented in your sample. So you have only low income group, low education level Muslims and medium level and high level Hindus. So the bulk comes from this group. So you see, the moment the religion changes, so does the education. So you have really not looked at all the cells. So you are basically comparing a low education Muslim with a high education Hindu and trying to say whatever difference you see is because of the religion. That will not be fair. So from this, you cannot really conclude anything. That's my point. I'm not saying you can conclude either for Hindu, against Hindu, for Muslim, against Muslim. I'm merely saying that if your data set is like this, then you have a confounding between these two factors. The linear algebra will remain happy, R will remain happy, but the conclusion will not be meaningful. So make sure all these things are properly represented and you are changing one factor at a time. If I have some observation here, Hindu and low income group, then you can compare the cleanliness of these two cells to get an idea about the difference between Hindu and Muslim. But here, there is nothing in this cell. So you are comparing this cell with that cell, which means you are basically changing both the religion as well as the educational level, and you do not know that the change that you see is because of this or that or because of simultaneous presence of both the changes. You have no way of knowing it. That is called confounding, and it is a good idea to try to avoid that. So this confounding is a problem. Now confounding can occur in two ways. One is when both the factors that are confounded are treatments, something that is applied by the researcher. Now that type of confounding is pretty rare because if you are applying, you naturally remember to apply all possible combinations, like the fertilizer and variety example. You would rarely apply only one kind of fertilizer to one variety and a different type of fertilizer to a different variety. You will know that you have to apply all possible variety fertilizer combinations. That's nothing very difficult and it rarely occurs. But it inadvertently occurs in situations where at least one of the factors involved happens to be a control factor that is beyond the direct influence of the experiment, or something like gender or medium of instruction and things like that, or the religion of a person. In that case, you use the technique called blocking to avoid confounding. So the idea is again very straightforward and basically like a common sense idea. Suppose you have some kind of a medicine and you suspect that its effect might be different for men and women. Then it is not just enough to collect a group of patients who are all that is a mixture of men and women. It is important that you carry out the experiment separately for the men and separately for the women. So if you just take a collection of patients who are as identical as possible with respect to everything else except their gender and the medicine that you are going to apply, and then you take half of them randomly and apply your medicine, and for the remaining half you apply placebo. That is not a good way of carrying out this experiment. Because in this case, it might happen that when you did that random allocation, most of the males got your medicine and most of the women got your placebo. In that case, you do not know if you see that there is any difference between these two groups, whether it was because of the gender difference or because of the treatment difference. So what you should do is that you should split it up into two groups. Take the men on one side, take the women on one side, then split these men into two roughly equal halves, apply the medicine and the placebo separately, independently. You also split the female group into two roughly equal halves and apply the medicine and the placebo. So whatever you do for this group, you do separately for that group. Then you can really do the comparison, because if you compare the placebo men and the treatment men, then you can see the difference between placebo and treatment, the gender effect remaining the same, similarly for women. And if you compare the treatment men with treatment women, then only the gender is changing, so you can get an idea about the effect of gender. So do not change both the things simultaneously. That's the main idea. Similarly, if age group is also an important thing, and if you have say 3 age groups, young, middle-aged, and old, in that case, you should split the entire thing into 6 different groups. That idea is called blocking. This is a block. That's a block, and that is the idea of blocking. So if you cannot control that factor like gender, at least you create blocks where within a block everyone is homogeneous with respect to that control factor, like everyone has the same gender. Similarly, there you will do it in 6 groups: young men, young women, middle-aged men, middle-aged women, and like that. And then you can apply. So that is the concept of blocking. What we have learned so far, blocking, that is one way of tackling confounding. So the main problem with confounding was that you were changing 2 arrows, 2 inputs to your black box simultaneously. And blocking was one way by which you can prevent this when one of your arrows or one or more of your arrows are what are called control factors. Like gender or smoking habit or age group, things that you are not administering yourself. Now, the very similar concept works even for the random error input, because that is also an input. Unfortunately, here you cannot just say that I will hold the random error fixed at a certain value while I will change the other input. Whenever you change any input and you take fresh measurement, the random error input will change. It is not under your control. So the idea of blocking does not directly apply to that random error input, but something less satisfactory may be done. And that is the idea behind randomization. The idea is, since the random error input will keep on changing, you can at least hold the other inputs fixed and allow only the random error input to change values. Now this takes 2 forms. The first form is called a repeated measures experiment. So it is like this. Suppose we are trying to understand the behavior of a spring. Our familiar example, we hang some weight from the spring and we measure the length. Then in the next experiment, we just carry out the experiment again from the beginning. We remove the weight, let the spring return to its original length, and then again we hang the same weight back on the spring. So the only thing that changes from the last case is the random error. So let only the random error change, hold everything else fixed. This is called a repeated measures experiment because you are repeating measurement with all the setups held fixed, and it is a very frequently used technique. We all know this when we carry out experiments in, say, a physics lab. Whenever we want to measure a length, we typically measure it multiple times. That is also an example of a repeated measures experiment. You are allowing only the random error to change. Of course, this is only half of the story. The other half should be, now you keep the random error part fixed and you change only your input. Unfortunately, you cannot do that. If you are able to do that, then you do not need any statistics at all. If you can keep the random error under control, then of course you do not need statistics. So we can't do that. So it is just sort of the one half of the idea of blocking. Now the same concept may be used in a slightly different way, and we have already used them in this way. It is when we are doing random allocation. Say you have got some 20 plots and you have got 4 varieties. So you have decided to allocate 5 plots to each variety. Then this allocation must be done randomly, because even if you believe that all your plots are as identical as possible, still you have to, so there will be some amount of variation, and you want to give everyone a fair chance for those variations. So you want to do a random allocation. So randomization takes 2 forms. One is repeated measures experiment, where the factor that we are working with is something that is either a treatment or something that we can hold fixed, and we have this random allocation idea where within a fixed number of objects you are allocating your treatment in a random way. Well, we have learned about various techniques, various concepts related with design of experiments. Unfortunately, all these techniques, while they are very common sense techniques, they often prove to be very expensive to implement. Say for example this case. Suppose we have this setup where we have got a system where I have got 5 inputs. Suppose they are all factor inputs, categorical ones, so there are got 5 inputs, and each input may be, say, so the first factor may have 5 levels, the second one may have 4 levels, and so on. We have got one output and the random input as usual. Now, if we want to follow all those nice principles, blocking, etc., then what you should do is you should try to change each of these factors one at a time, keeping all the others fixed. And also you want to keep all the factors fixed at all possible combinations and just repeat the experiment to allow the random error to show itself. Which means if you have K1 level for the first factor, K2 level for the second factor, and so on, and you want to do a repeated measures experiment where you want to repeat it K times, in that case you need how many? You need K1 times K2 times K5 times K many measurements. So if you are working on these systems, so whatever the systems are, they may be mice, they may be students, plots, patients, whatever, you need K1 times K2 times etc. up to K5 times K many such systems, such units, and they also must not be just any units, they must be very well structured. So there must be exactly K1 of them which has the first level. So there must be certain number of things which must have the level of the first factor equal to this, the level of the second factor equal to that. So they must be very well organized. Like if you want something like young and old, and male and female, and smoker and non-smoker, urban and rural, then you need a certain number of people who are rural, who are young, and who are smokers, and who are females, come from village. So you must have a sizable sample from that group for each one of them, and that becomes often well nigh impossible and almost always very difficult. In that case, what people do is that they will systematically or carefully, cleverly flout one or more of these nice principles such that the final conclusion still remains valid in a limited sense. And how all those things are done, that is the subject called design of experiments that you are going to learn in the next semester. But the main mathematics, the main statistical tools that we use in design of experiments for the analysis, that remains linear models. So whatever we discussed in this video today is about how you go about applying linear models to real life. So as I have said already, these things do not influence your linear algebra, they do not influence how you write your code in R. So even if you flout all these things, linear algebraically it is a valid model, you can run that code in R and get some output, but statistically they will not mean anything.